All right. Hello, everyone. Welcome to this week's Tech Talk. The Tech Talk series is the University of Idaho Library's Data Hub's attempt to put UI community members in touch with resources, topics, issues that either affect or may help them produce scholarship in this sort of information and digital age. So to that end, we have Luke Sheneman here with us today, Head of Research Computing and Data Services, and he is going to talk with us about vision transformers. So have at it.
Okay, thanks. Let me share my screen here. Go to the first slide. Okay. Okay. Can you see my slides? Are you seeing the right version of it? Okay, great. Okay, yeah, thanks everybody. Like Norman said, I'm Luke Sheneman. I'm the Director of Research Computing and Data Services within the Institute for Interdisciplinary Data Sciences here on campus. Our unit supports
That's here.
Oh, okay.
Just a heads up.
Oh, you're seeing the wrong one.
Yeah.
Okay. Give me one sec, guys. Sorry. We're looking at the wrong screen on Zoom, apparently. Why is this always the problem? From start. You're still seeing that version?
I was thinking about it.
Let me. Sorry, guys. I'm gonna reshare my screen. I think what I'll do is just share my whole desktop. And then do.
Hey.
Okay, all right, let's just do this. Okay, sorry, backing up. So my unit does a lot of stuff with respect to research computing. So we support most of the high performance computing resources here on campus. That includes things like the Falcon supercomputer, local cluster computing resources and storage and that sort of thing. We also do a lot of web application development, database development, things like that. And increasingly lately, we've been doing a lot of stuff with artificial intelligence. As you know, there's a lot of research happening on campus with respect to AI across a lot of different fields, a lot of different departments, colleges, and domains. Some of that has to do with large language models, which of course have been really popular lately, as the popularity of ChatGPT kind of proves. But also a lot of stuff having to do with computer vision and dealing with images as well. And so today I'm going to talk about vision transformers, which is kind of a new development in computer vision that sort of replaces or at least augments the use of convolutional neural networks, which was kind of the previous thing, and it still is. But vision transformers have gained in popularity in recent years, and I'll be talking at some length about them. And they intersect large language models to some extent, and I'll explain that in a minute because it's fundamentally the same architecture. So computer vision, there's some basic tasks that are really common in computer vision. In computer vision, we're really just teaching computers how to see, right? How to see and interpret the world. And so there's some very specific discrete tasks that computer vision algorithms do. Those include things like image classification. Given an image, tell me what is it of, right? Okay, this is a picture. This is an image of a cat, for example. Classification plus localization, not only tell me what's in the image, but where it's at. Put a bounding box around it. You can do object detection where there might be multiple objects in a scene and you want to be able to detect all of those discrete objects and then assign some sort of label to them, like this is a cat, this is a dog, right? So you're doing that sort of localization and classification, but you're doing it in multiple instances in the same photo. And then instant segmentation, which is you go beyond the bounding box and you actually find the contours of the edges of the object itself within the image. And so cats and dogs, for example, you can define really carefully their outline. lately, you can do some really impressive things with things like pose estimation, not just for humans or but also for animals, and that's useful for all sorts of things: movement science, wildlife studies, all sorts of stuff. Lately, you can also do things where you are merging the idea of language models and computer vision models into one thing, where you can either generate an image from text or, given an image, have an algorithm describe what's in the image and caption it. And so that's another version of computer vision, right? Describe to me in English what's in this picture. And we'll talk a little bit more about that and some of the algorithms to do that. Some of the more advanced things that are happening with computer vision, obviously autonomous driving, where you're doing a lot of object detection and segmentation of entire scenes, and you're doing it in real time and then making decisions based on what you see. Remote sensing, where you're looking at either satellite, aerial, or drone imagery, or aircraft imagery, and then you want to do things like identify what something is, do segmentation, for example, to say, okay, this is this kind of tree, and this is a river, and this is a road, and be able to do that automatically without having to hand label things. And obviously in biomedical imaging, computer vision is incredibly powerful. And in fact, it's been quite some time now that computer vision algorithms are outperform humans on detecting, for example, cancer tumors in a lot of cases in people. And so it has become an invaluable tool in diagnostics in medical imaging. And there's lots of other examples. There's also generative AI. So these two examples are, not real people, right? These are synthetic people. The first is from just a text to image algorithm from Midjourney. And the other is a text to video example from OpenAI and their new Sora model. It's gotten to the point where now with Sora, you can generate up to a minute of 4K video at 30 frames a second and hyper realistic scenes just with text prompts, right? And that's super fascinating. And in order to do that, in order to train the model to do that, there's computer vision methods involved, right? It has to be able to look at training data and understand what's in it semantically and be able to create models that can generate things like that. Okay, so I'm going to go over some basics just really quickly. I've done this in previous lectures as well, but I'm going to be a little bit faster about it this time. But I'm going to talk about just sort of neural network basics. We'll talk a little bit about convolutional neural networks, which are particularly useful for image applications. Then we're going to talk about transformers in general, and then switch to the vision transformer, which is the main topic of this talk. And then we'll talk about a hybrid convolutional neural network and vision transformer, which is also becoming quite popular. And then I'll actually show you code in which we will use a hybrid CNN transformer to classify images as to whether they're cats or dogs. So kind of a simple hello world kind of computer vision thing. But it's a good test of how well our system does. So neural network basics, right? So if you look at sort of traditional neural networks, where you have where you're basically trying to model the nervous system or the brain, and you have basically neurons. And so if you look at this picture up here in the upper left, you see these white circles represent neurons, and those neurons are connected to other neurons with edges. Okay, and they're organized into layers. So in a traditional fully connected neural network, you have an input layer and an output layer and some number of what they call hidden layers. And it's called a fully connected network because you can see that in every layer, every node or neuron is connected to every other node and neuron in the previous and subsequent layers. And the idea is that you can, there are values associated with the edges. Those are called weights. And there's values associated with the actual neurons themselves, and those are called biases. And those are trainable weights and biases. Those are trainable parameters in your model. And they basically come together like this, where you have two inputs. Here you have X1 and X2. connected to this node Y over here. I'm sorry, this purple box is the node. And it's connected with this edge that has a weight associated with it. X2 has another weight associated with it. And there's a bias. There's another trainable, learnable parameter there as well. And so you're trying to optimize those values ultimately in a larger network in order to achieve some sort of goal, whether that's image classification or something along those lines. But you end up with hundreds of thousands or millions of these nodes organized in layers and organized in this way. You apply, you take these weights and biases and you apply what they call an activation function, which is to say, given these inputs, put them through this function, and that function defines what the output of that neuron will be to the subsequent layers, okay? And in these really large networks, you basically optimize these iteratively using a method called gradient descent, which is just an optimization method for quickly navigating kind of a fitness landscape to tweak those knobs and dials associated with those. For computer vision, this would be a really simple example of using a fully connected neural network to do a computer vision thing, where you take this 28 by 28 image of this number 8. It's an image, but you can serialize it into a linear set of values just by reading the pixels left to right and then down. And so this 28 by 28 matrix of intensity values becomes just this linear set of inputs to this network, right? And there's 784 different unique inputs now. And you have some number of hidden layers, and at the last layer, you have your labels, right? And so in this case, we're doing handwriting recognition. Given this figure, tell me what the most likely output on the output layer. Okay. And so through a process of optimization through gradient descent repeatedly by using labeled training data, we can tweak those knobs and dials in those weights and biases and train a model fairly easily these days to do handwriting recognition with a really classical neural network. And in fact, this code in the upper right-hand corner in Python is all you need to do to define and train a two hidden layer neural network that is quite good at classifying handwritten digits. The interior layers, these hidden layers, what they do in theory is extract features, right? They extract higher order features. So given sort of raw intensity values in your input pixels, those hidden layers start aggregating, especially if there's fewer nodes in your hidden layers than there are in your input layers. You have to start aggregating features together into higher order things. So you start aggregating them into things like edges, dark spots, light spots. If you're looking at trying to identify human faces, that might then translate into parts of faces like eyes and ears and noses, and then eventually into discrete facial structures. And so it's in those hidden layers and the way they're organized that feature extraction happens. But the issue is with fully connected neural networks that they take that sort of serialized input, right, where you kind of lose that two-dimensional representation of your image, right, because you're turning it into one long one-dimensional array of pixels. And so one of the things that you could do, and this is what is most commonly done now, is you apply convolutional filters. And so a convolutional filter is simply a set of operations that you perform in 2D by convolving or by iterating a small matrix, which we call a kernel, over an image and performing essentially matrix multiplication to derive a different image, a new image in which you've extracted specific features. And in this particular case, this Sobel filter that I'm showing here, when you convolve this over an image, we'll find the edges, right? Because it's highlight, in this first matrix, we'll find I think the horizontal edges, and this second one will highlight the vertical edges. And so it's an edge detection filter. And that's one way that you can extract features before you pass them through a neural network. And you can do that explicitly with something like this. Or you can use a convolutional neural network in deep learning, which is to say you don't define those filters, those edge detection filters. You have the model discover them and discover which filters are the most important to extract the features that are most relevant to your objective. And so in this case, this is again a 28 by 28 MNIST image. We extract by convolving filters across it a set of feature maps. And then one of the things, those feature maps are the result of those filters, right? And so you can pass any number of filters. In this case, we have 6 separate discrete filters that we train to extract different features from this original image. And then you often do a thing where you shrink the size of your image, usually in half. It doesn't have to be in half, but usually in half, and you extract even deeper features. And the idea is you want to get those higher ordered features, those ears and eyes and noses and faces. And to do that, you shrink the image but extract deeper feature maps. And then from there, you can linearize that final set of deep feature maps into a fully connected network, and then do your decision making as far as what the most probable digit is. And so that's a really common classifier, convolutional neural network right there, that will tell you what that digit is. And it combines convolutional layers and fully connected layers to do that. So let me now talk about transformers. So basically, convolutional neural networks were the best approach for image processing up until very recently, and some would argue still are. But transformers came on the scene in 2017 in this sort of seminal paper called "Attention is All You Need," and this was from Google Research, where they were actually doing a problem with large language models, where they were looking at the problem of language translation. I think they were translating English into German or something like that, and they proposed this completely novel architecture for handling language, which they called the transformer. And I'll go in. We're going to talk mostly about that model now, but the transformer is what underlies all of the current large language models that you're probably most familiar with. That's like ChatGPT, Anthropic, Google Gemini, and other things like AlphaFold that does protein folding. It works on sequences. So what are proteins? They're sequences of amino acids. Our genome is a sequence. We can do all sorts of cool things with transformers. Music is a sequence, right? We can do all sorts of cool things with it. But the thing that makes transformers work is this thing called attention. And we're going to go into great detail and actually implement attention mechanisms from scratch in Python here. But the gist here is that attention allows the model to identify automatically what are the most important parts of the sequence that it needs to pay attention to in order to maximize whatever objective it's trying to get to. Okay. And that attention mechanism is very mechanistic, and it's pretty simple when you get down to it, but we'll go into that in a minute. A transformer can be an encoder, where you have an input sequence and you want to encode that into something. That's what we're going to implement today, is an encoder-only transformer that encodes an input sequence and gives you some sort of final output. In our case, whether it's a cat or a dog. You can have decoder-only transformers, which would be like ChatGPT. ChatGPT is a decoder-only transformer, or the GPT models, which is to say it has a context window and a sequence, and it just iterates on its own context window. It produces the next token and then kind of rinse repeat. The thing about transformers is that they're very parallelizable, meaning that you can do a lot of the operations with these models much faster than you could with prior language models like recurrent neural networks or long short-term memory networks, which we won't go into. But the other thing about transformers is that they seem to scale infinitely, which is to say, as long as you give it, the more data you feed it and the more compute you give it, the more powerful these networks get to be. And so when you look at what like ChatGPT can do, and Gemini and Anthropic, Claude, they're the result of scaling these transformers to like global scales, right? And massive data centers looking at all the data in the world, right? And these transformers seem to have no bound into how high they can scale. Other methods hit bottlenecks of some sort. They start plateauing eventually. Adding more data doesn't seem to help. Adding more compute doesn't seem to help both transformers. So far, there's no known limit to how far these things can scale, and they seem to scale linearly with compute and data. So what are the different components of a transformer, right? So what I'm showing here is what's called an encoder-decoder transformer. This was in the original Attention is All You Need paper where they were doing language translation. They were doing encoding of German and decoding to English, right? So they were doing language translation. And what we're going to do, and so the encoder part is on the left, and the decoder part is on the right. In previous talks I've given where we actually implemented a large language model from scratch, we did a decoder-only transformer that was able to learn Shakespeare and emit Shakespeare, right? Here, we're going to do an encoder-only transformer. So what is attention? So self-attention is actually relatively straightforward. You look at all of the tokens, and tokens are like the words or subwords in your context window, in your sequence, and you compare it to every other token in your context window. And basically you're looking to see how important the other tokens are relative to any given token in the overall context, in the overall general sequence. And I'll go into detail on how that's computed. But you can see that it's an n-squared algorithm, right? If your sequence length is of sequence length n, this attention mechanism is n-squared because you have to compute every token against every other token. But the thing is, you can do it in parallel on things like GPUs, and so it's actually relatively fast. It's still computationally intensive when you start talking about really long sequence lengths. Just kind of go over this really quick. I know I'm talking about language models, but it's really relevant to the computer vision stuff. So this is a decoder-only transformer, and these are sort of the distilled components of it, right? You have your what are called your token embeddings, which are sort of the semantic representation of all of your tokens in your entire vocabulary, combined with positional encodings, and I'll talk a lot about that in a minute. But then you go through the self-attention mechanism, which I just sort of demoed in that little animated GIF there, and then you identify, you basically transform your input tokens into a context-aware form, and then pass that through a feed-forward, fully connected network, and then ultimately get some sort of output. But the thing is, you can have multiple attention heads, and you can have multiple layers stacked on top of each other. And the multiple attention heads at every layer are looking at different parts of your input sequence. Okay, they're not looking at the entire thing, or I'm sorry, not your input sequence, but your embedding vector, your semantic embedding vector. They're looking at different parts of your semantic embeddings. But then you add multiple layers, and each subsequent layer is kind of like in a convolutional neural network. Every subsequent layer stacked on top of each other. You see this one, why does it keep doing that? This says 12x right here. That means we're in this particular thing, we're looking at 12 different transformer blocks stacked on top of each other. Every block takes the input of the prior block, takes the output of the prior block, and operates on it. And so every subsequent layer is looking at higher order features, right? The first block works off of your basically your tokens, but the next block looks at the result of a transformer on that. And then you get more and more abstract, more and more sort of composite as you go up. And the result is, with language at least, you can get this really nuanced understanding of language where you can develop an understanding of humor and sarcasm and all sorts of things, because you actually have enough of these transformer blocks to be able to pull that out. Okay, so transformers are exceptional with language. They do really well. There's no end in sight so far as to how well those transformers work. But what about images? So in 2021, there was a paper also from Google that came out called An Image is Worth 16 by 16 Words, Transformers for Image Recognition at Scale. And in this paper, they claim that we show that the reliance on convolutional neural networks is no longer necessary, and a pure transformer applied directly to sequences of image patches can perform very well at image classification. So this was the seminal paper on vision transformers that came out not that long ago, like what, 3 years ago, right? Okay, but convolutional networks are really good on images, like really good. Like we can see pretty well with CNN. So why do we need vision transformers? Well, okay, so let's look at the pros and cons before we dive into vision transformers. So the pros of convolutional neural networks is that they're really efficient for spatial data, right? That you convolve these matrices over images. It's really sort of efficient on modern hardware. You don't need a lot of data to train relative to vision transformers. And it's really good at local feature extraction, right? Because you're applying these small matrices over areas and extracting really local features and kind of building those up as you shrink your spatial dimensions. But the cons is that because of that, they also have a limited receptive field. They often don't look at the whole image. Convolutional networks don't usually look at the entire thing. They're looking at parts of the image. And they're somewhat less flexible than vision transformers because for any particular application, you may need a different CNN architecture, right? So you might need to like rethink carefully how you design your CNN for any given thing. Whereas a vision transformer can almost be applied copy and paste to almost anything. Vision transformers are aware of the whole image. They scale as transformers do really, really well. And they're flexible. One architecture, like I said, can almost be like copy and pasted or cookie cuttered to all sorts of applications. The cons are that they're expensive to train in. They're very data hungry. The more data you give them, the better. But sometimes you need to give them a lot of data. And they're a little bit harder to understand, I think, than convolutional neural networks, as we'll dive in. I did want to talk a little bit about CLIP. So CLIP is a to create a common embedding space, right? So this is a common semantic embedding space. And the thing about that is now start interrogating photos. You can develop captions from photos. You can develop algorithms that you can do sort of zero-shot classifications where you can give it an image it wasn't necessarily even trained on, but it has enough understanding of the semantics of what's in the image that it can make extrapolations and analogies and tell you what's in it. It's the basis of generative AI systems like DALL-E and Midjourney, are things like CLIP, where you're combining language and vision and images that share a common semantic embedding space. And you could do things like image similarity search, right? You can look for similar images given an image. And that's how like Google image search works, right? You give it an image and it has the semantics embeddings already pre-calculated for like all the images on the internet. And so it's able to quickly find things that match your image. You can do things like content moderation, like, okay, is this porn? Is this, whatever. It's really good at that sort of thing, just out of the box without any sort of special training. And so it's a fantastic, it was kind of a watershed thing, and it's trivial to use, right? This amount of Python code is all you need to do to interrogate a photo to figure out what's in it, right? It's really trivial to use. And so super powerful. And, I'm hoping to do more stuff with it in the future. I don't know if you can see this, but one of the things that this shows is how much better CLIP does at object recognition than a really high-end convolutional neural network, right? And so this is against on the ImageNet, which is this really large collection of images that are used for like large-scale image classification studies. CLIP does as well as ResNet 101, which is a really large convolutional neural network. But when you start doing other things like, okay, well, rather than actually look at that, let's look at pictures of, actual pictures of bananas from the ImageNet data set, we do as good as ResNet. But if we look at, like, I don't know, sketches of bananas, it does way better than a ResNet on that. If you look at adversarial examples where you have bananas in weird situations, the convolutional neural network ResNet that was trained on the ImageNet network just fails horribly. It gets like 2.7% correct or something. I mean, it's just, I don't even know how that's possible, but Clip does really well. So it understands the semantic sort of content of the image and can do really well in sort of these weirder use cases. Okay, but wait. So transformers only work on sequences. We talked about that. They can only work on sequences with that self-attention mechanism. So how in the world do we get it to work on an image? Because an image is not a sequence, right? Well, this is the trick. You carve up an image into a bunch of patches. So in this case, we took this image of a dog and we carved it up into a bunch of, say, 16 pixel by 16 pixel patches, non-overlapping patches. That then, once they're into patches, then you could serialize those patches into a sequence, okay? And you see that sort of down below. Okay, so now you can convert an image into a sequence of patches, and once they're a sequence, we can use transformers on it. So now we can start thinking of patches as though they're tokens, okay? And they're not tokens, but they're the equivalent of tokens. And so, if you had a 512 by 512 image, and you carved it up into a bunch of 16 by 16 non-overlapping patches, you'd have 1,024 patches. So that would be a sequence length of 1,024, which is a reasonable sequence length for a transformer model to work on. If you look at large language models now that operate on 100,000 tokens or more. So an image becomes a sequence of length 1024. Okay, but one of the issues with transformers is they're not actually aware intrinsically of the position of any token in the sequence because they do everything in parallel all at once. So what you have to do is you have to tell it explicitly where a particular token is in the sequence. And there's a number of ways to do that. One is that you can just create a trainable, learnable vector that basically is incorporated with your sequence embeddings that it learns over time to train that to represent location information. But the original way, in the original transformer paper from 2017, what they did was use this thing called sinusoidal encodings, which is you apply alternating sine and cosine waves at different waveforms or different wavelengths for different positions in your sequence, and you apply those across your embedding vector. And I'll talk a little bit more in detail about that. But what you're basically doing is you're taking this sinusoidal pattern that you're seeing up here, and you're applying that over your embedding vector. And you're literally just concatenating or adding, you're just adding actually the values in those positional encodings to your semantic embedding vector. But the transformer is smart enough over time to learn that pattern exists and will use it to understand the relative positions of tokens within the sequence. And this is actually what we used in code that I'll show you here. So I've talked about these embedding vectors. What is that? So an embedding vector, is basically in large language models is where you just take a token and you convert it into a series of numbers, right? A series of floating point numbers. Usually it's highly dimensional. So like in GPT-3, I think there's 12,000 or so dimensions in their embedding vectors. That means every token, which is a subword, has a semantic dimensionality of 12,000 different dimensions. And so it's super crazy. And you could think of those embedding vectors actually as like vectors, like in physics where you have an amplitude and a direction. And with that, you can do things like compare them using things like cosines. You take the cosine of two vectors, you get their distance, and you can figure out what's more similar or more distant from other things. And that's how You can do similarity search with large language models or with images. But I just wanted to give you a little understanding of what these embedding vectors are, because we're going to use them for images as well. For large language models, you can actually have an embedding layer, right? Which is a two-dimensional tensor, which is the size of your vocabulary. And the vocabulary in GPT-3 is about 50,000 subwords, multiplied by the length of your embedding vector, which is about 12,888. So that's the size, that's your embedding vector, and that's a concrete thing that's part of your model. But in patch embeddings, the vocabulary of possible 16 by 16 8-bit patches is some crazy big number, right? There's no way for you to have a discrete embedding layer, right? The vocabulary is too big. There's too many unique patches. So what you have to do is create what they call a continuous embedding. And a continuous embedding is really just a function. It's in this case, it's actually just a little neural network that learns the function, which is, how do I map like a 16 by 16 patch to an embedding vector, right? And it just does it dynamically for all embedding vectors. And that neural network is trainable. It's trained as you train your network. And so that's a simple solution, and it works quite well. So this picture actually describes the overall architecture of a computer vision, a vision transformer, where you take your image, you carve it up into discrete patches in a series. You compute the, you have this linear projection, which is that does the continuous patch embeddings. You compute your semantic vector, and you apply now your positional embedding. So now you have your positions and your semantic embeddings, and then you can now apply your transformers and ultimately lead to an end result, in this case, a classification. This is kind of showing the same thing, where you take, I'll just kind of reiterate here, you take your image, you carve it up into patches. Each patch, you pass through your patch embedding function that you learn as you go. And in this case, the embedding vector length, the number of dimensions, is I think 768. In our code that I'm going to show you today, I use 1024 as the embedding vector size. But we have this function that we learn that basically takes these 16 by 16 patches, converts them into a linear embedding vector. We apply our positional encoding. And so now we have our input into our transformer. Our transformer takes those inputs, which are our patch tokens, our patch embeddings, and all they do is transform them. And one reason why they're called transformers, they transform them into a new representation in which they express sort of the relative importance of every patch in the context of all the other patches. And that's what it learns through the self-attention mechanism. And then we apply, there's a very specific token that we add to the network that we use then to pull out a classification. And I'll go into detail about that in a minute. I think we kind of went through this already. This is just showing an encoder block and the fact that you can stack encoder blocks on top of each other. In our code that I'm going to show you today, I have 32 different layers, and each layer has 8 attention heads. Just for some context. So this is actually, this little animated GIF is showing you the self-attention mechanism. This is showing you the self-attention mechanism for a 3-token sequence. Okay, and you can see on the bottom are your input sequences. These are sequences with embedding vectors of only 4 dimensions, right? So this is a really toy example. In reality, I'm using embedding vectors that are 1024, and I'm using sequences that are much longer, right? But ultimately, this is what it's doing, and this is kind of going so fast you can't watch it. But let me go through really quickly, kind of what's happening. So you have in the self-attention mechanism, you have your 3 input layers, input token embeddings, and you have associated with every token, with every head, you have a key, a value, and a query vector. Okay, so those are vectors that you don't necessarily have to be the same size as your embedding vector. Often they're a little smaller. but they're trainable matrices, they're trainable weights that you can learn as you're training your network. And you're basically taking every token has a query, and every token has a key. And so for say I'm looking at input number 1 here, I'll take my query vector and I will apply it to the key vector of every other token in the sequence. That will give me what's called an attention score. Then I take that attention score and I multiply it by every vector's value matrix. And then from there, I simply sum up all of these to get the different outputs for any given token. And so this attention mechanism is the core of GPT, of vision transformers. It's what allows all the tokens to look at all the other tokens. And it does these through just matrix multiplication and dot products. And again, you can have multiple heads. And so what you do is each transformer block can have multiple attention heads, and each attention head can look at a different subset of the input of the input embedding, actually, I should have said. And so it's splitting up the work sort of of multiple attention heads. So they're all looking at kind of different parts of the semantic interpretation of a given token. And then they're aggregating through a concatenation layer that aggregates the results of those multiple heads into one final answer. So it's kind of like you have a bunch of things that are looking at partial solutions and bringing it all together into one before giving a final answer. And again, each one of those heads has a value, a key, and a query vector. Okay, so this is a really great image, and we kind of went through another example of this before, but this is a really great image that kind of brings it all together. And I'll just go through it really quickly and introduce the CLS token. So the input image, you carve up into patches. You pass that through a learnable linear projection, which is basically calculates a function that converts that into an embedding vector. You apply your positional encodings attached to each position. You pass that through your transformer encoder, which is some number of these in some sequence, right? And you end up with your transformed tokens, which reinterprets each token in the general context of the overall sequence, right? What we do, though, for the vision transformer is we introduce we add 1 basically to our sequence length, and we add this new embedding, which is called the CLS token. I think it stands for classification in this case. What this is the transformer model will actually compute that classification token as a function of doing the self-attention, and use that, and you'll have some sort of embedding that's like this highly dimensional representation of that token, but that token represents and is optimized for your task, which in this case is image classification. And you pass that through an MLP, which is just a fully connected network, to get your final classification of, in our case, dog or cat, right? And so that step right there is sort of critical. And I'll show you in code, and we got about 15 minutes left. But before I do that, I wanted to introduce this idea of hybrid convolutional and vision transformer networks. And the idea with that is, we already know that convolutional neural networks are excellent for localized feature extraction, right? They're really good at that. Whereas vision transformers have a global receptive field. They can see the overall image. So what if, instead of working off of patches of pixels, we work off of patches of extracted features, where the features are extracted through those convolutional layers. And so that's what we actually implement in code, and I'll go over with that. And so what we're going to do is we're going to build a hybrid CNN vision transformer that can tell dogs from cats. So just really quickly about the data set that I used for this, there's this Microsoft cats and dogs data set, which came out in 2007, actually, as part of a CAPTCHA, right? As the idea in 2007 was that computers would never be able to tell the difference between dogs and cats. In 2008, it was a solved problem, but that was what came out. So basically, this data set has 25,000 labeled images of cats and dogs, roughly split evenly. Half of them are cats, half of them are dogs. They're not localized or anything. Some of the cats are you know, part of a bigger picture. Some of the cats are like the main thing. Some of them are really challenging because, you know, there might be multiple cats or multiple dogs in a scene. In fact, some of them are impossible because there's a dog and a cat in the same picture. But it's this great rich data set that you can just download from Microsoft. It was solved at 83% accuracy with support vector machines. This is pre-convolutional neural networks back in 2008. And in 2014, it was pretty much totally solved by Pierre Sermonot, who was a student of Yann LeCun, who is the head of AI at Meta. He used an approach using his own model architecture that solved it to 99.914% accuracy, which I think is the best out there. And I think people kind of stopped after that. But people still use this as kind of a hello world kind of thing. But for a long time, there were competitions on who could do better on the dog and cat classification. And you could think, you know, the idea is humans can do this pretty easily. They can do it at 99% accuracy within 30 seconds, right? But a computer has a real hard time, and you know. But now we can solve it pretty well. But so this defines sort of the model architecture that I used, and this is basically what my code shows, and I'll go through my code in a second. But basically, it takes a 512 by 512 image that has a depth of 3, right? So red, green, blue. It applies a series of two-dimensional convolutional filters, or convolutional layers that extract feature maps. And at the same time, or right after that, I do what's called max pooling, which is I shrink the spatial dimensions of the image by half. So I start out with these 512 by 512 by 3. I run it through this first convolutional layer, and I get a 256 by 256 spatial image, but with a 64 deep feature map, where hopefully we're starting to extract things like edges and bright spots and things like that, right? Then we do it again, and we get down to 128 by 128 with a depth of 128, and do it one final time to get down to an image that's only 64 by 64, but with a really deep feature map. So now we're kind of building up our feature map. So hopefully by that time, we're looking at things like, I'm hoping, you know, these things are kind of a black box, but, you know, maybe it's a cat ear, maybe it's a cat tail, right? Those kinds of features you'd hope are starting to get extracted at that level. And then from there, with that latent feature map, right, that's what we then cut into patches. So I cut those into patches that, you know, since now we're only dealing with 64 by 64 spatially, I cut them into 8 by 8 by 256 deep patches. And then I apply that trainable projection function that converts it into a vector embedding. Okay, that's 1,024 long. So this vector embedding represents that patch at lower dimensionality, right? It's a one-dimensional it's a one-dimensional vector, in the sense that, you know, it's just this array of numbers, but each position in there has a value. And so you can think of it as a 1024, you know, embedding. And then I apply my sinusoidal positional encodings, just add those together, run those through my encoder, transformer encoder. I use 8 attention heads per layer and 32 layers. We get our CLS token embedding as an output from that, run that through a simple neural network, and that will give us, you know, the end, you know, the last two, the final layer of that neural network has 2 nodes. So one represents cat and one represents dog, right? And we just pick which one. So I will say that I just wrote this and trained this weekend and got about 95% accuracy, which I thought was pretty good for, you know, an initial stab. I think I could get higher. You know, I cut out a lot of data, maybe 10% as validation data as I was training the algorithm, that, you know, that's important data that didn't get included in the training. But I think it turned out pretty good. So let me bring up the code and we'll go through that real quick before we run out of time. So let me bring up this.
And it's all right if we run a little bit over, as
Okay.
long as everyone else is okay with that.
All right. Yeah, so it's just so it's you know, Sheneman, github.com/Sheneman, which is my last name /ViT. ViT is the shorthand for vision transformer that everybody uses. I'm going to go through the model code really quickly. You can see that, right?
I'm not sure. Yeah.
Yeah. Okay. So let me go through. Yeah. Now I'm in a different place.
Yeah, we can't see that on Zoom.
You can't see what?
It's just GitHub.
Oh, just GitHub. Okay. Maybe I'm looking at the wrong thing. Let me stop sharing and let me share again. You see it now? Okay. All right. So yeah, so let me go through this really quickly. The important thing, there's two basic files. One's called model.py, which defines the architecture of the hybrid CNN. You want it bigger? I think. Why is that? I'm sorry, I'm having technical issues.
You can also, pull some chairs closer or something.
Yeah, no, I think. Okay, everybody's seeing the same thing, I think. Okay, let's try this again. Okay, is that okay? Okay, so yes. Basically, I did this all in PyTorch. So PyTorch is like the most popular machine learning framework right now, deep learning framework. And PyTorch makes this pretty easy to do. I define first a bunch of sort of hyperparameters that define kind of how many layers I have. Remember, I had 32 different transformer blocks. Each transformer blocks had 8 attention heads. My embedding dimension is 1024. My patch size is 8 by 8. My image size that I start with is 512 by 512. And my latent dimension, that is after I apply the convolution and max pooling, gets down to 64 by 64. Okay, so the first thing that happens is this convolutional encoder. The convolutional encoder basically does a series of convolutions. It takes a RGB, a 3-channel input tensor, and applies 64 filters, right? So we extract a 64-layer deep feature map. We apply batch normalization. I find that applying batch normalization after convolutional layers always helps with training. Then I take the next one, which I take basically building off of that that now 256 by 256 by 64 tensor. I do the same thing. I get I get 128 deep feature map, then 256, and at the end of all of this, right, I end up with the 64 by 64 by 256 deep result, which is what I use to then turn into patches and then run through the transformer. Let's see. I do apply dropout at the end of this. Dropout is used to help mitigate overfitting, model overfitting. So you're basically inflicting a little bit of brain damage to your networks occasionally so that it learns to like generalize better. And you don't tend to overfit your data as readily. Okay, so this is what defines the patch embedding, right? So what this does, basically, we define a couple variables like our image size and our patch size and the number of patches, right? And the number of patches here, I think, is 64. So in a 64 by 64 grid, cut it by 8 by 8, you end up with a 64 long sequence length. So our sequence length for our transformer is really short. It's only 64 long. This line right here is the magic function that computes the embedding vector. What it's doing essentially is taking the 256 deep feature map that I had at the result of that, the convolutional layer, and I'm extracting it into something with an embedding depth of into a feature map with an embedding depth, with a depth that is the same as our embedding dimensions, right? And we do it with kernels that are the size of our patches. So basically this is transforming our 64 by 64 by 256 tensor into one big vector that is the length of our embedding vector. And so this one line right here, this convolutional line, is what computes that continuous function that computes the embedding vectors. I do a dropout here as well. In the attention mechanism, this is kind of where all the math happens, right? So this is where you define, for every attention block, we define, what our embedding dimension is, how many heads we have, and then we define our head dimension, which is how much of the embedding vector length does each head pay attention to. I have 1024, a length of 1024. I divide that evenly by the number of heads I have, which is 8. And that's what I process on. We define our query key and value vectors as sort of a matrix that we then pull those things out later in the forward pass. And then we actually do an additional projection step at the end of the attention block, which just gives it another opportunity to learn to extract more, learn more from the attention mechanism before going to the next level. And so here's where we extract our query key and value vectors out of that matrix that I defined up here. This is where we do our dot products of our queries and our keys. Remember that animated GIF where we were doing all the math? This is what happens in the forward pass of the attention mechanism. And this is all you need to do to define that sort of self-attention. And then what we do at the end of that, at the end of all the attention blocks, we have a multi-level perceptron, just a neural network that is used to inside the transformer block, but after the attention block, it basically takes the output from the self-attention and runs it through another set of layers. And in this particular case, the idea is that you get your embedding dimension as the output of the attention block. You bump it up to an expanding middle hidden layer that's 4 times the size of your embedding layer. And that gives it extra expressibility to find additional sort of nuance in your embedding space. And then you shrink it back down to your embedding vector. So you're trying to tease out more relationships from just your embedding, sort of your transformed embedding vectors, the output of your attention mechanism. And then we run that through, so the transformer encoder kind of puts it all together into a transformer block, right? So we have our attention mechanism followed by our that multi-level perceptron that I just defined, and you have a couple normalization layers. The important thing to keep in mind is you also have what they call skip connections. Skip connections are an important part of transformer blocks. They allow you to sort of route around either the attention mechanism or the multi-level perceptron, or to take some combination of both by summing them. So all this does, the way that this is written here, it allows you to sort of bypass parts of the transformer block. And that's really important for being able to do the gradient descent for these really long neural networks, is to allow a mechanism for residual connections. And then the vision transformer component kind of brings all of that together into one big thing. So let's just go through it real quick, and you'll kind of understand how it's put together. So we have our convolutional encoder, which does the, takes our initial image and converts it into a feature map or a latent space. Then we take, then we get our patch embeddings, which is basically, the method for extracting our embedding vectors from our patches in our sequence. Now, here's the CLS token. This is where this is introduced. So this is simply a token, it is a vector, which is the length of our embedding dimension, but it's just one vector, right? And that is something that we add later on, I think in our forward pass, we concatenate it to our existing embedding. That extra vector is what you pay attention to at the very end to determine whether or not what you have as output. Is it a cat or is it a dog? So what they call a CLS token is sort of the critical piece. Here is where we also define our sinusoidal positional encodings. And so in the forward pass, you can see, in the forward pass, you can see we do our convolutional encoder, our patch embeddings. We define our CLS token. We add our CLS token to our existing sort of set of embeddings for our sequence. We iterate over all of the layers in our stacked layer transformer blocks. Then at the very end, we pass that CLS embedding. We extract it right here, and then we pass that through a classifier, which is just a simple neural network that we define just as a sort of this linear thing here. This classifier takes an embedding vector of length embed dimension and converts it into, why it's doing that? It converts it into, gosh darn it, basically the two classes, right? The number of classes that we have in our training set, which is 2, cat and dog. Sorry, that's done. Right. Where was I? Oh. Right here, this classifier. It's just a linear layer that takes your entire embedding dimension and collapses it into cat or dog. And then at the very, you'll see now, let me switch to the main code real quick, where we do the training, and then we'll kind of wrap up. I will say I ran this to train for about 2 days. It was slow to train. This is a big network, right? And I ran it on an RTX 4090 GPU, which is pretty fast. But it was such a large network that I could only do a batch size of 8, so it was like kind of slow to go through 25,000 images to train it on for every epoch. I also did what you'll see here. I did a lot of data augmentation as well, so that every time an image came through, it was augmented. It was either rotated or shifted, or color was changed a little bit, so that it would the same pictures of the cats and dogs were almost never presented exactly the same way twice, right? They were always manipulated in some way, allowing the model to generalize a bit better. So here's where you can see I set up these transformations that do the data augmentation. So things like, first of all, I resized every image to 512 by 512. Some of the images were bigger than 512 by 512. Some were smaller. Almost none of them were actually square, so that you're going to get some amount of warpage, right? As I did that. You could also center crop them, but I found that just resizing them tended to work okay. So I did horizontal flips randomly, rotations up to 10 degrees either way. I jittered the color a bit, did some kind of perspective distortion stuff, just to make sure that there was a lot of variability, and as the images were getting trained on. And then when I did validation, so in other words, in validation, you're basically at the end of every epoch of training, you test your model against data it wasn't trained on, so you can see how well it's doing against data it's never seen, and that's the validation step. And I did less augmentation for that. And so there's this val transform, which is for the validation step. So real quick, basically, if I had a GPU, I set the device to CUDA, which just means I'm using the GPU. I instantiate the vision transformer. So remember, in that model.py, I had this vision transformer defined, and so I instantiate it here. And so now this is my model, right? I make sure that it's moved to the GPU. If I'm picking up from where I left off and I want to load a previously saved model, I can do that here. I define my criteria, which is cross entropy loss, which is often the one that's used for classification problems. I use the Atom W optimizer, which is really common for transformers, and I'm not totally sure why, but with a learning rate that's also common with transformers. So here's basically how I trained, right? I turn the model into training mode. And then for all images and labels in our train loader that I defined above, we send those to the GPU. We zero our optimizer in between batches. I call the model itself. So I give it the pictures and I get the results out. I calculate the loss and then I run my optimizer, right? And I kind of keep track of my sort of aggregated loss into accuracy as I go. And that's about it. And so, like I said, I ran this for a couple of days on the entire data set. About 20% of it I left out for validation, and I got about 95% accuracy, which is good. It's not state of the art, but for a couple of days with this simple model, it did pretty well. But I think as an example of how vision transformers work and how you can combine convolutional networks and vision transformers together, I think it's a good sort of hello world kind of example of how to do this stuff from scratch. I will say that all of what I went over here was kind of doing it from scratch so you could kind of see the concepts. But if you really want to do this in the real world and you just have an application you want to do, there's vision transformer libraries out there that you can just sort of import and use. But you don't really learn much from doing that. So I didn't want to go over that. But yeah, Hugging Face has a whole vision transformer library that you can just kind of import. And it's probably more efficient in a lot of ways, but you don't learn anything by using those. So anyway, with that, I'll take any questions anybody has.
I'm also going to pop a little survey in the Zoom chat for people who want to give feedback on the talk.
Okay. I think there was
It was a
mistake. Okay. Yeah, that's fine.
So feel free to pop questions in the chat, unmute yourself, whatever you prefer. Anything from y'all?
Yeah.
The positional encoding.
Okay.
So what you're doing there is you're just kind of putting in a pattern that the AI learns to recognize and use as relationship with where
exactly.
The other patches.
Exactly. So what I ended up doing, and you can see it in the code, my positional encoding, I use a one-dimensional positional encoding, right? I use the sinusoidal waveform thing, but I did it assuming a one-dimensional sequence. You can do a two-dimensional positional encoding, which I think would actually be better for images, where you basically do it across the x-axis, you do it across the y-axis. And so then every position has some combination of those results. And people do that too. And I think I'd probably get better results, honestly, if I did that, because then you don't lose the sort of spatial, X, Y dimensionality in your positional encoding.
Square.
Yeah, exactly. I mean, I think it kind of infers this, width and height of your image given the positions, but the positional encoding, but I think you can be more explicit and be a little more effective if you use two-dimensional positional encodings. But like I said before, a lot of people, instead of using that sinusoidal positional encoding, what they'll do is they'll just create a layer which represents a learnable positioning encoding, where the neural network actually like puts values in there that get added to the actual, embedding vectors that teach it. You kind of learn as you go how to represent positions the best. Instead of using that sinusoidal way, it comes up with its own thing as it's training. And so if you look at like GPT-3, for example, if you look at the actual architecture of, or sorry, GPT-2, which is open source now, that's what they do. They use trainable positional encodings. And in some ways that would have been easier than the sinusoidal, but the sinusoidal thing is maybe a little more efficient because it doesn't have to figure it out, but maybe not as effective because it's kind of arbitrary, kind of the way, it's just kind of a man-made sort of way of doing it. But that's what was in the original transformer paper, was the sinusoidal encoding. But yeah, it's just a pattern that you overlay.
You can extend that to three-dimensional data as well.
Yes. Oh, yes. So vision transformers, you can convert video into sequences too, right? And so if you look at like Sora, which is OpenAI's image thing, right? If you read their tech paper, they talk about working off of space-time patches, which are, three-dimensional, I think it's X, Y, and time, right? And so they would need positional encodings with that extra dimension. And so, yeah, you could apply any number of dimensions to those positional encodings. Yeah.
So I know you had a question, but there's a quick one in chat.
Oh,
that I'm
okay.
hoping we can get to is, can you recommend any books on these transformers or resources more generally?
I can recommend ChatGPT. It's a good resource. If you want, it will write one for you. So it's a good way to start, and you can just ask questions of it. I don't know about books, but there's definitely lots of resources. Like I said, there's vision transformers that you can just use from Hugging Face. There's lots of papers if you just Google them on vision transformers, and a lot of them have code associated with them. So it's a good way to learn. But I don't know about books. Yeah.
All right. Now.
Yeah,
Or-
I think you already answered my question. What I was going to ask is, like, if you have a sequence of words, the transformer is very efficient to learn that encoding of the position.
Mhm.
The position that's with the picture, it has two-dimensional data.
Yeah. Right. And so I think if I were to, if I had the time to tweak this to try to classify cats and dogs better, then I would, that's one of the things I would address first, is I think I would address the positional encoding to make it two-dimensional, a little bit more explicit. I think that would help. The other thing that I would probably do is add more layers to the projection function that takes a patch and converts it into an embedding. I think right now it's just a simple convolutional, one-step convolutional step, which seems to work pretty well. But I think if you were to make it maybe multiple levels, convolutional levels, that would give it a little bit more learnable parameters that might be able to like extract more things before making that final projection. But yeah, definitely dealing with the multidimensional positional encoding would be number one. Yeah.
The other thing I was like, when the transformers were first developed, it was developed for translating from one language to the other. And when you are translating from one language to the other, you were just feeding, you were just asking the transformer to generate part of the sentence and feeding it to itself to generate the next token.
Yes.
So for that reason, in language, you don't want your next token to influence your previous token.
Right.
So that's why you mask your
Yes.
outputs, and then you feed it to the transformer next time.
Exactly.
Do we have any kind of problem like that here? Do we mask it?
I don't think for classification there's a need to do that because it's not. So I'll have to say, like, encoders only, they're not generative, right? There's no way for an encoder only transformer to be generative. But once you add a decoder, then you have the opportunity to be generative, right? And when you start generating things and predicting things that might happen in the future or later in the sequence, then masking becomes important. And in fact, when I was developing this, one of the things that I think became kind of clear to me was like the application of this kind of stuff to things like image outpainting and inpainting, right? So you'd have an image, you take some amount of it out, and you train the network to predict what's missing, right? And it's almost like next token prediction, but in this case, it's next patch prediction or missing patch prediction. And so you're able to predict at least the embedding vector that's missing. And then you've got to be able to translate that into pixel space at some point with another network or something like that. But that would be a good problem where you'd have to do some kind of masking like that potentially. And with outpainting, where you're trying to like, you go out, you expand a painting out and start, filling in what's on the borders, and you can kind of zoom out, right? That might be almost auto-regressive in that sense, and you might need to do some masking there. But I can start to see how that works. This next patch prediction kind of thing. Yeah.
So with time is one of your video. When you bring it back into
Video space.
video space, which is back to you. This is an opportunity for the resulting output to actually influence itself forward and backwards out. I'm just being more philosophical about it, about how Sora's output looks so much better than even just a little frame. Because it knows backwards. It has parallax. It gets to learn from its own parallax, and so it can come back and is it doing that? It's like, wow, I should correct this wrinkle.
Yeah.
There was some kind of there was a I didn't sleep last night. I only have got sleep jars.
Yeah. Like occlusion or something. Yeah.
You need to learn from the patching of time,
Right.
what's going on behind all the occlusion as well.
Yeah. So I think with something, I don't pretend to know all of what's happening under the hood with Sora, but reading their technical paper where they talk about space-time patches, right? You imagine that that's their token. That's what they're using as tokens, essentially, are these space-time patches, which are small two-dimensional things with multiple frames associated with them, essentially. And they're converting those probably into linear embedding vectors, probably very long linear embedding vectors that can express a lot of semantic sort of understanding of what's happening in that space-time patch. But then they've got to have a way to translate that back to video, right? And so there's some neural network or part of the transform, I'm not quite sure, that does that projection of, from that embedding vector back to 3D. And yeah, I think because it's a transformer that has many layers, it's able to look at things at different scales, right? Different levels of abstraction. And so it's able to understand, I don't know how deep their time goes in their time dimension, but they understand, sort of longer time steps, right? Like that occlusion example that you mentioned, where something passes in front of something and yet it persists in subsequent frames later. That means that their time dimension must be long enough to bridge that gap. Yeah. But ultimately, I think, just like in the 2D case where you're doing like in-painting or out-painting, I think in video, it would be similar. It's just you have to have some mechanism to project from that embedding back to video, at least to video chunks or patches. Yeah. Anyway. Okay. Thanks, everybody. Appreciate it.
So much.